So it gives you the force that is experienced by a small particle. When I say small, what I am effectively trying to refer to is that the Reynolds number defined based on the particle size and the characteristic time scales at the scale of the particle to be negligible. So with that you have this total description of what the particle force is. Now there are different things that you can do obviously. So first thing is, you can say that, alluding to Newton's law, saying that this force should be equal to mass times acceleration, which means mass of the particle du dt is equated to everything that is there on the right hand side. If you prescribe the background flow u infinity, then you will have an equation to solve for the particle velocity, but there is also another quantity to solve for, which is the particle position, which is given by this, right. The center of mass of the particle moves due to the particle velocity. So all of these quantities that you are evaluating, there is a center of mass of the particle that is there, right, xp. So if you say, for instance, you were ignoring the fraction term in these, you will write this as u infinity at x equals xp comma t. You are going to write this as du infinity dt x equals xp comma t. That is the background fluid velocity evaluated at the particle center, background fluid or the undisturbed fluid acceleration evaluated at the particle center, if you ignore the fraction part to it. So this is the set of equations that you need to solve. Now even with all the assumptions that you have made in arriving at that, you ignore fraction and all that being there, you can see the biggest challenge in this particular equation is, it is an integro differential equation, right. You have a derivative of the particle velocity which is coupled with an integral over that quantity. So a numerical calculation can become quite expensive, because in order to find the particle acceleration and then update its velocity, imagine that if you want to find out that I know what is the particle velocity right now, and I want to find out where is the particle's velocity at a later point in time and thus find its updated position, I need to know what is the particle acceleration at this point in time. Think of it as a very crude numerical exercise. If you, everything on the RHS, so you can write this as MP particle velocity at t plus delta t minus particle velocity at time t divided by delta t is equal to particle acceleration. So up is actually in our notation u bar. So particle acceleration at time t, right. Now this quantity actually involves you doing an integral of the fluid and particle acceleration all the way from the point in the past to right now. So you have to store that data. You have to store that data and then basically continuously integrate it whenever you are trying to find an updated particle velocity and then an updated particle position, right. If you just think of it as a trivial first order Euler kind of an integration, this is what you have to do. And even to do this, you have to store massive amount of information of particle acceleration and fluid acceleration along the particle trajectory for all points in the history. So the particle is moving in some way, this is the particle coordinate xp of t. So at every point, imagine discretizing this, at every point you need to store information of particle acceleration, fluid acceleration, fluid velocity, and then as you move and you are here, you will require the information all the way until the past because of that non-local nature. That is the part which makes it computationally quite expensive. there is one more point here, that how would all these things change? We have made one strong assumption here, which is the assumption regarding Reynolds being negligible, right. We have solved all of this, and at every step I said we will linearize the equation and we are going to solve the unsteady Stokes equation for the disturbance. The equation for the background flow is the Navier-Stokes equation. We never make any assumption regarding the background flow, whatever is the background imposed flow. What we are saying is that the disturbance is governed by the unsteady Stokes equation. So now the question is, how is this actually going to change if there was some finite Reynolds effect? Now you have already had some experience in trying to understand what finite Reynolds number does. So the one thing which you know is that the moment you introduce Reynolds, the quasi steady Stokes drag is going to change from minus 6 pi mu a. So it is u bar minus u infinity at x equals xp into 1 plus 3/8 Reynolds. This is the quasi steady Stokes drag, and this is now the correction due to Reynolds. And how is Reynolds defined here? Reynolds would be mu modulus of u bar minus u infinity into particle radius by nu. Reynolds is defined based on what is the slip of the particle with respect to the fluid at that location. It is in some background flow, right. So this is a correction that you know. You know that there is going to be a correction due to Reynolds where the drag is going to get higher. The lowest drag you experience is in Stokes flow. So this expression, you could write it as, let me just write it as the Faxen kind of a term, into some function of Reynolds number. And you can use different expressions from asymptotic expressions, or you can use also empirical relations. So there are various kinds. So there is one which is quite popular. I might be getting this spelling wrong. That's the Schiller-Neumann. I think is the Schiller-Neumann correlation. So that would be phi is 1 plus 0.15, Reynolds based on diameter 0.687. So Reynolds based on diameter is twice u bar minus u infinity a by nu. This is a very popular drag correlation that people use, which tells us how the drag actually, the steady drag, how does it change with Reynolds number going from Stokes drag. But there are few other subtleties which are not as simple as just this steady Stokes drag. If you take the other limit, this is a bit of a jump, but if you take the inviscid limit, you have a spherical particle which is moving in a fluid where there are no viscous effects, not necessarily potential flow. It is an inviscid, so it can be rotational, but it is inviscid. And if you try to calculate what is the force that it is going to experience, now we already know that if you were to do potential flow, then there would be an added mass term, that if u was a function of time in a background flow that is also varying with time, then you would get an added mass term. But if the flow is rotational, then you are going to experience a force which is mf du infinity dt. Now that is quite similar to what you had here. Right? Du infinity dt, basically rho dV gives you the mass of the fluid, and then you will have half mf du infinity dt minus du dt. U bar is the velocity of the sphere and u infinity is the imposed flow, and then you are going to have half mf u infinity minus u bar into the background vorticity. Now this looks similar in some ways, but it also has a lot of differences. Now this term is quite similar to what we had in our Maxey-Riley equation. This term also looks similar. This term is not there. And it is not surprising this term is not there, because this term is actually a nonlinear term, right? What about this term? Is it identical to what we had in Maxey-Riley? So the minus sign is basically because I wrote du dt first, so that there is no negative sign issue. But in Maxey-Riley-Gattignol equation, that term is mf du infinity dt minus du bar dt. So is there a typo where I am trying to write capital D and small d? So what I mean by this capital D and small d is capital D dt is a material derivative which is obtained by following a fluid particle, whereas small d dt is a rate of change or a material derivative which is obtained while moving along with this finite size particle, or the particle which is not a tracer particle. So the point is, if I draw streamlines and if I draw the path taken by that spherical particle, they are not going to coincide necessarily. So when you are making measurements of a quantity, as you move along the black curve, that gives you capital D dt. So d dt of u infinity is the fluid acceleration, which is what we typically understand as fluid acceleration, that is measured along a fluid parcel, whereas small du infinity dt is the fluid acceleration as viewed by the spherical particle. And as you can see, both are not the same. They are different, right? The difference between the two, and this is an important point, that the two will not be equal necessarily for all cases. So when you do this exercise, this is what the inviscid theory is, and this came out in a set of papers by Orton and co-workers in 92, I think 1987, 1988. There was a series of papers which actually focused on this added mass term in a rotational inviscid flow. And this we are not going to get in the Low-Reynolds number problem, because we are not doing that nonlinear term. So as you can see that these are inherently terms which have to do with the nonlinearity part. So we are not doing that. So the added mass term that we have in our version of Maxey-Riley, that has the fluid acceleration. The fluid acceleration that you have in the added mass part is the fluid acceleration as viewed by the spherical particle, not as viewed by the fluid parcel. So with this, I will finally conclude that you can now try to a bit of it is empirical, a bit of it is based on some rigorous part, that what will happen when you do finite Reynolds Maxey-Riley. So, finite Reynolds Maxey-Riley-Gattignol would have a force that would be f of t, the undisturbed fluid part, which you already know, that continues to be there. If there was nothing else in the problem, this would just be capital du infinity dt, that is the fluid acceleration, minus g, and then you will have a 6 pi mu u bar u infinity and then a drag correlation. This could either be the Oseen correction or the Proudman-Pearson correction, or it could be a Schiller-Neumann correlation if you want to use something from the fits of the drag force. Then you have your added mass part, where you are trying to use Orton's expression, where it is the difference between the acceleration of the particle as measured along a particle trajectory with the acceleration of the fluid as measured along a fluid trajectory. And then finally you have your history force, now this kernel that I have written down here, this kernel, as I said earlier, is 1 by root t minus t prime, right. So, 6 pi mu a square, square root pi nu, and then that is root of t minus t prime. Now, this root of t minus t prime, as I was discussing when we got all of this started, is actually trying to tell you that if there is a path along which particles move. So, there is a spherical particle which is moving, and you are trying to basically find out that what was its acceleration at all points in the past, and you are trying to add them together with a certain weight, which is that 1 by root t weight, and find what is the net history force that is experiencing. But then you also know that there is a certain length scale which scales as nu by u bar, beyond which inertia is comparable to viscous forces. Convective inertia, let me be more specific, that convective inertia beyond a certain distance from the particle is as important as viscous forces. So, you cannot be ignoring the rho u dot del u term. This cannot be ignored beyond a certain distance. So, when you are trying to add all of these acceleration with a certain weight, you are erroneously saying that they have a very strong influence, because that kernel is a very weakly decaying function. It is 1 by square root of your past time. If you imagine that you are at some point here in the past, and this time instant was some t star, and right now it is time t, then the weightage of this acceleration is 1 by square root t minus t star. So, even if t star was significantly in the past, the weightage is a 1 by square root weightage, which is not a very rapidly decaying function. But because of this wake that forms and this aspect of inertia becoming important, this weightage actually is not as important as 1 by root of t minus t star. It is rather, it decays as 1 by t minus t star square. It decays quite rapidly. So, if you go back to what we had done for the wake calculation, so for the contribution from the wake, the importance of that acceleration decays inverse quadratically rather than as a inverse square root, and you can see that an inverse square root is a very weak decay compared to an inverse square kind of a function. So, you can come up with kernels which basically switch. If I were to plot k versus tau, it will switch from something that has a minus half behavior to something that has a minus 2 behavior. So, there will be a cutoff time beyond which it is going to transition from the purely viscous decay to a viscous inertial or the Oseen kind of a decay or the wake mediated decay. So, this is again a set of work that was done by me and Adrian, but again I mean these kernels are derived, and also their numerical implementation does not get necessarily very simple. Numerically they are quite a challenge because it still remains an integral differential equation. So, it is not that it becomes trivial in terms of numerics, you are still solving integral differential equation, but roughly speaking that aspect of how rapidly the past contributions are decaying, that gets altered because of inertia. That is a point that is quite important. So, with all of this, if you just focus on what history is actually doing and you take up a problem of just settling, this is what was from last lecture, no background flow. If you do not forget everything about background flow. So, the equation is m du dt is equal to m g minus 6 pi mu a u, right. Do we have any other term? Minus half m. So, this would be actually mass of the fluid. So, this should be rho f by rho p into m du dt. This is the added mass part, and then you have one last term which is 6 pi mu a square minus infinity to t 1 by root pi nu t minus t prime du dt evaluated at t equal to t prime dt prime. Now, if you just did the calculation with Stokes drag, you just did this, your equation is du dt is equal to g minus 6 pi mu a by m, right. Now, 6 pi mu a by m can be written as 4 pi by 3 rho p a cube. So, this is 9 by 2 mu rho p a square. Is that okay? What is the dimension of this quantity? Again, mu by rho p is not the kinematic viscosity of the fluid. This quantity is not, I guess, because this is density of particle, but it does have dimensions of, what is the dimension of this quantity? Length square per unit time, right. So, this has length square per unit time, the denominator has units of, so it has inverse time. So, this object I can write it as some inverse time. So, tau p is 2 rho p a square by 9 mu, okay. So, this equation can be written as du dt is equal to g minus u by tau p. Then I have a term which is half rho f by rho p du dt, and then here this is 6 pi mu a by m. So, this becomes a by tau p into minus infinity by t 1 by square root pi nu t minus t prime du dt t minus at t equals t prime dt prime. So, this is equation without history and added mass, and this is the equation with history and added mass. Now, this equation is quite simple, right? It is a first order differential equation in U. So, if you solve this equation, what do you observe? U of t is equal to, what is the steady state value of this equation? Can you find the steady state without solving this equation? At steady state, what is the value of du dt? 0. If it's steady state, the velocity is constant, acceleration is 0. So, at steady state the solution is g tau p. So, now you see that g tau p is basically your settling velocity, the Stokes terminal velocity, and then based on your initial condition you are going to get a part which would be, so let us say you started out with some velocity, it would have an exponential u of 0 exponential of minus t by tau p. So, it would achieve its steady state right. It should basically, there should be, now here I think there should be a exponential of minus t by tau p and then u of 0 of exponential of minus t by tau p. So, there should be, this is the homogeneous part and this is the particular part. So, at steady state obviously it achieves the terminal velocity, but the approach to steady state, let us say it was starting from rest. The approach to steady state, if you plot the velocity from rest, it approaches the settling velocity exponentially fast. Whereas with the history term, if you were to look at this, again you can solve this equation, there are methods of solving this equation, I am not going to focus on the method for solving this equation, but as it decelerates, right. So, basically the particle starts to first increase its velocity and then it is basically slowing down. So, finally, the history force is going to act in opposition to gravity. So, what it will do? It will slow down the rate at which it is going to approach the steady state. How quickly it approaches steady state, that is basically going to get altered because of the presence of history. So, what was earlier an exponentially fast process will now become an algebraically slow process in terms of how it approaches the terminal velocity. So, this tau p, the time scale that we have, tau p is known as the relaxation time scale. It is the time scale over which the fluid gains or loses the momentum. So, here it is achieving a steady state, but imagine that there was no g, there was no acceleration, then the solution is u of t is u of 0 exponential of minus t by tau p. If you did not have any g, then you release a particle with some velocity, it will come to rest because of viscous resistance, and the time it takes for it to lose its initial velocity by a factor of e, that is the relaxation time scale. And you can see that the relaxation time scale is going to be significantly large if the particle density starts to become quite large. So, if you have heavy particles, then tau p is automatically going to, you take two identical size particles in the same fluid, but if you make the particle density heavier, then tau p is going to get larger, and tau p becoming larger means I am going to achieve my terminal state, or I will achieve my steady state, or I lose all my momentum more rapidly than an identical problem of the same size particle in the same fluid but of lower density. So, this is the quantification of how much inertia you have. What is the degree or what is the amount of inertia that is there in the problem. So, this entire approach of doing this kind of closes, and everything that we have done here is for a spherical particle. So, you can take some of these and extend it in the context of particles of other shapes, other geometries, etc. But roughly the principle remains the same. Roughly what we are doing regarding these forces mostly stays the same. So, there is one more thing for single particle which we will pick up in next class. So, as of now, whatever I have done here, I have included the effect of Reynolds number in two ways. One was in the correction to drag, and the other was the modification of the history kernel. These are the two ways by which I have included the effect of Reynolds number. But when we did the calculation of finite fluid inertia, we saw that there is obviously, if there is a particle that falls, there is a wake that forms behind the particle. So, in next class what we will touch upon is that are there any other additional forces that would exist in this particular problem. So, if you go back to one of our earliest lectures where we said that if there is a particle that is falling close to a wall, it can neither go towards the wall nor it can get repelled towards the wall. You use linearity and reversibility. If there is a particle in a channel flow, if you place the particle, it does not move away from its streamline. These were the arguments which you have done using linearity and reversibility. We are going to revisit some of them. Again, I will keep it qualitative, that how does inertia change these configurations. So, with this I will end today, and we will meet on Thursday. So, as I said in last class, we are going to meet also on Friday, and next week we will only have lecture on Thursday. Tuesday, I think Monday is anyway a holiday. Tuesday I won't take class. So, this week